have been obsessed with TikToks that involve science. I mean, that's not really shocking here, is it? But these are just really visually pleasing and scientifically so satisfying. And I had to put 4 of them to the test. So today we're going to do some that you can even try at home and dig into deeper once you see how they're done. This first one though really makes you feel like a wizard of some sort, because you're going to light this candle, blow it out, and then relight it from a distance away. Okay, so for this first one, we're going to light this candle. We have to let it burn until it hits this waxy point. And once you start seeing wax, you have the ability to blow it out. It's critical that you have some sort of wax, because this is what happens and creates the magic. Let's see if we can do it on this one too. Yeah. This magic works because when you light the candle, the heat from the flame vaporizes the candle wax. When you blow the candle out, that wax is staying vaporized in the air, and when you quickly apply heat, you can ignite the wax and use the vaporized wax to relight the wick of the candle. So using the vaporized liquid wax and turning it into a gas that's flammable is going to be critical for our next experiment. Okay, this one to me is incredibly satisfying, partly because I'm a meteorologist, but also because it's super mind-bending if you don't know what's going on. So all you're going to need is a candle, a graduated cylinder, or some kind of glass, and then another glass to hold your water in. This one is really satisfying, and we've actually done a lot with it on the channel before, but I wanted to put my own spin on it, if you will, that involves alcohol and fire, which is fantastic. So, but before we get there, we have to understand the basic principle of how this works and how we're creating a partial vacuum. So you set it up like this. You have your awesome candle here. You're going to put it in your water. There's no tricks here. This is literally just water. We're going to light that candle, and then you're going to take this graduated cylinder and you're going to turn it on top of this candle. And this is when the magic really happens. It's so simple, but it's so awesome. Okay, so to understand how this works, there's really basic principles happening here. All you're doing is creating high and low pressure areas. This is going to make the air want to travel to certain places. So what this candle does is it heats up the air column that's in this graduated cylinder. Once that air is so warm, it's going to then be moving all over the place very quickly and expand. When the air inside this column cools, it's going to shrink. Because this air can't go anywhere, it's creating a low pressure system within this graduated cylinder. So we have a low pressure. Where's the high pressure? Because anytime you have a low pressure, you have to have a high pressure so there's equilibrium. Our planet and everything really loves to be in equilibrium. So you have high pressure that's on the outside or within this glass, if you will, and what that does is that high pressure pushes down and forces water onto the inside. So this distance from here to here where the water is basically this graduated cylinder equalizing itself. Now if we take this off, the graduated cylinder releases it and it's back to its normal happy pressure. Most people think the water rises because the candle is using all the oxygen, but that's not true. The candle's playing a part here, but it plays a part in heating the air that's within our graduated cylinder. And then when it cools off, it basically creates that low pressure system. Now in meteorology, we have low pressure systems and high pressure systems, and they're all so important. But what happens if we create a more intense low pressure system within our graduated cylinder? To find out, we're gonna use this big guy right here. So creating this more intense low pressure system inside the graduated cylinder, we're gonna use a reaction that's a little bit more aggressive. Rubbing alcohol and a lighter within this graduated cylinder and then tipping it over and trapping it is going to give us a way bigger pressure difference and allow it to be a little bit more aggressive. Okay, yeah, we have a smell this time. There it is. It's so cool. Look at how much like the alcohol, like our little candle, it just kind of like bloop, up a little bit. This one, like, it sucked the whole thing up. It displaced this much air and like pressure, and the high pressure and the low pressure. It's just so cool. And it didn't involve a candle. Okay, let's do it again. That's what I was looking for! That was so cool! We mastered it! That's awesome! Look at how much freaking water it displaced! This is crazy. In meteorology, low pressure systems and high pressure systems are basically everything. When you have low pressure systems, you get really volatile reactions, like we got all this water sucked up. That's when you get your rain, your thunderstorm, your lightning, everything, because the atmosphere is so angry. And then normally after that pressure system moves off, you get this nice, relaxed, cool, and just equalized environment, which I mean, this is a perfect demonstration of that. So low pressure systems, angry, gross, bad weather. High pressure systems, happy, outside weather. And then when they all pass, you got an equalized environment. That's your meteorology lesson for the day. Rubbing alcohol, lighter, and jugs are just way too much fun, which is why our next one involves this guy right here. Another experiment that I love is the Woosh Jug. It's basically the opposite of what we just did, where instead of us trapping the alcohol in fire reaction, this time we're going to let it escape and feed itself. So through this opening right here, basically we're going to coat this jug in alcohol, and then we're going to light it, and then there's going to be blue flames everywhere. But as the reaction is happening, air is going to be being sucked into the jar and circulating. So that's how the flame is continued to be fed. Whoosh! Whoosh! What I love about this reaction, honestly, this was kind of a baby one, so we're going to do it again and see if we can make it a little bit more aggressive by using a little bit more alcohol. But I love the very pleasing effect of you seeing it basically using all of its fuel down the whole sides of this jug. It's just really awesome. This is one of my favorites because the science behind it is simple. The heat from the flame causes the gas in here to expand rapidly. And the thing about rubbing alcohol is that it already evaporates quickly, so there's a lot of it in a little concentrated environment. And then when the gas is squeezed out of the little nozzle up here, it causes that whooshing sound. So the displacement of air and the gas rapidly heating and trying to escape all go to cause this awesome, cool effect. Whoosh! And you can feel the heat on the outside of it too. And I mean, there's excess down there that's not even used, which I think is so cool. Speaking of gas, this next experiment uses actual gasoline, and I honestly think it might be one of the coolest and also the most annoying. So using this gasoline and liquid nitrogen, we're going to explore the Leidenfrost effect. And this drives me crazy because it feels like that DVD screen where it's like bouncing around everywhere and it never hits the corners. That's what this reminds me of. And it works because the boiling points of these two liquids, or whatever they want to be, are at two extremely different points. So let's go ahead and check this out. There it is. You can see them bouncing around. Look at them. Choo, 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 choo. Literally none of them have hit a corner yet. It's just so fun to watch. So because these two are separated by such different boiling points, a vapor is instantly created. And that's what causes this thing to seem like it's floating across the surface of the gasoline. When the liquid nitrogen hits the edges of our pan, it boils again, and that's what sends it off in a different direction. So if this all were to become the same temperature, the effect wouldn't happen anymore. But because the temperatures are so vast and so different, they just don't want to be together. Kind of like oil and vinegar, but also kind of not. The Leidenfrost effect is the same thing that kept Grant safe when he threw a cup of liquid nitrogen at his face. And I don't have the guts to do that, so I'm sure you can check it out somewhere around here on the screen somewhere. It'll be there. But that's all we have for you guys today. If you want to see us react to cool science videos or you want to see us test them out, send them to us and we will check them out for sure.